Hi everyone. As a wrap up to our learning the idea of the derivative, I want to talk about second derivatives, and then where we're headed next is to start learning shortcuts for taking derivatives that will allow us to avoid the limit definition on a lot of our basic functions that we run into all the time, and then combinations of those as well. So this starts off as usual. First page is a preview activity. So if you want to pause and work on thinking about what is going on in this situation, this is supposed to be the graph of a position function of a car. So units measured. So this is thousands of feet. Distance cars traveled in thousands of feet, and this is time in minutes. So if you want to walk through and think about what's going on in this situation and work on drawing a velocity function, and then work on drawing another function based on that, and then check back in, I'll walk through that as well. Okay, so first we're just supposed to talk about what's happening to the velocity of the car. And velocity, I think this has come up, velocity is speed, right? But it has a direction associated with it. So velocity can be positive or negative. So what I'm seeing is, remember, velocity is related to position by the fact that it's the slope of the tangent line will be the velocity of the object. So this is a car. So if we draw a tangent line, we estimate its slope. The slope of that tangent line should be how fast the car is traveling. So it looks like we start off stopped, or at least close to it, and then the tangent line would get steeper as I go. So this is the car, the velocity is increasing. So velocity increases over, what are we supposed to do? 0 to 4. Definitely 0 to 4 it increases, and then we're supposed to go 4 to 8, and 8 to 10, and 10 to 14. Okay, so those are our chunks. So from 0 to 4, tangent lines are getting steeper, so the car is speeding up. From 4 to 8, it almost looks like a perfectly straight line, which means our slopes are not changing, or at least not much, which means the velocity isn't changing. So the car's speeding up, and then it's traveling at least approximately at the same speed for this whole thing. And then from 8 to 10, my tangent line starts to flatten back out again. So this appears to be slopes decreasing, velocity decreasing, which means the car's slowing back down. And then from 10 to 14, it looks like I have a horizontal tangent line, which is slope 0, which means velocity 0. So it looks like the car is stopped here. It's stopped at 12,000 feet from wherever it started, but definitely stopped. Okay, so we are supposed to sketch a graph of s prime of t, so the derivative of this thing, and we just described its slopes fairly carefully. So slopes start at 0, which means down here, this is my s prime. My y value should start at 0, and then they increase for a bit, and then they stay fairly level. We don't have a vertical scale here, but we could kind of count this out. Through here, it looks like we go over, this was 4, yeah, so this is over 2, up 1, 2, 3, 4. Okay, so over 2, up 4 is a slope of about 2. So if we say this is 2, our slopes are getting bigger and bigger and bigger, and then they're kind of leveling off at 2 from t equals 4 to t equals 8. So this should be our level spot. Okay, so we're speeding up, our slopes are increasing, and then they level off for a little bit, and then we're slowing down and coming to a stop from 8 to 10 seconds. So we're slowing down fairly quickly, and then we're stopped all the way to 14, slopes 0 all the way to 14. So there's what s prime looks like. C wants us to explain what the meaning of s prime is, and I've kind of already been saying that. That's our velocity function, right? So the slopes, which is what s prime would give us, represent the velocities. If s prime is positive, then the car is moving away from its starting point. Its distance is increasing. If s prime is 0, that means the slope is 0, the velocity is 0, so the car isn't moving. Okay, so now that we have this velocity function, we're going to go ahead and rename it v of t. So the derivative of position is velocity. And we are supposed to describe the behavior of the velocity function in words. When is it getting bigger? When is it staying the same? When is it decreasing? Stuff like that. So if I walk through the slopes of the velocity function, they start out small, maybe 0, I don't know. This is fairly approximate, so we're definitely getting approximates here. But it looks like we start out with 0 or small positive slopes, and then they get bigger for a while, and then they level off for this whole stretch. We have slope 0. And then the slopes become negative and more negative, and then they level back off to 0 again. So it looks like v is increasing during the first 4 seconds. V is constant from 4 to 8 seconds. V is decreasing from 8 to 10 seconds, and V is constant from 10 to 14 seconds. So using that, we should be able to duplicate the process that we did to get this graph in the first place. We should be able to say, let me grab green, so this is going to be V prime. We can kind of approximate the slopes that we're getting on this graph, and we can translate them over here. So I start with small positive or maybe even 0 slope, and then it increases for a bit, but comes back to 0 by the time we hit 4 seconds. So slopes are positive for a bit, and then they come back to 0. And again, this is already approximate, so exactly how steep this is, I don't know if that's a huge deal, but we could try and kind of count it out over 2 up 3-ish. So 1.5, so maybe just slightly higher. This is 2. Okay, and then the slope stays 0 pretty much all the way until we get to 8 seconds. And then from 8 to 10, it's negative, and it gets fairly steep in the middle. Maybe -3. So this, I think, is going to be steeper than what happened over here because we sped up over 4 seconds, but we're slowing down over 2. So this negative might kind of jump down here a little further. Okay, and then the slope for the last 4 seconds is 0 again. Okay, so again, this is rough sketch, but something along those lines should be what you end up with. Okay, so we're supposed to figure out the meaning of this new function, v prime. So what we have here is that this is a velocity function, and its units, on the original function we had thousands of feet and we had minutes. So here we'll still have minutes, and here as well we'll still have minutes. In none of these have we changed the meaning of the x value, the t value. But we are changing the meaning of the y value. Well, this was thousands of feet, this was distance. This is supposed to be slopes of the original function. So a slope here would be, rise would be change in distance, and run would be minutes. So there's our velocity. So this is going to be thousands of feet per minute. And if we repeat the process and we're trying to calculate a slope from this graph, so here I said it was roughly over 2 up 3. That's over 2 minutes up 3,000 feet per minute. So the slope of that would be 3,000 feet per minute divided by 2 minutes. This is thousands of feet per minute, which you can abbreviate down to thousands of feet per minute squared. So I'm going to move the page for a second. So basically, every time you do a derivative, you're going to take the units on your y-axis, and they get divided by the units on your x-axis. Okay, so we had thousands of feet per minute, and then that whole thing is per minute again. So the reason that we can do thousands of feet per minute squared is that that's the big division. So this becomes thousands of feet per minutes times minutes is the minutes squared. The meaning of this is acceleration. This is how fast your velocity is changing per minute. So if my velocity was 1,500 feet per minute, and it's increasing by 1,000 feet per minute, that means in the next minute I'd expect it to be 2,500 feet per minute. So it's the rate of change of the rate of change. It would tell you about how fast your velocity is changing. Okay, so that's the end of preview. Thanks for watching.